Oh, hello everyone to our seminar today on interval methods and control engineering. And it's my very great pleasure to welcome Sara Ifqir today. Sara did her master's and also PhD studies at the University of Paris-Saclay, and she defended her PhD thesis in the year 2019. And I'm especially happy to welcome Sara here because before that, she also did some research there at the university in Rostock, where we also collaborated on the design of interval observers. And after defending her PhD thesis, she moved on as a postdoctoral researcher to the University of Bordeaux, where she stayed until August 2021. Yes, and more or less in parallel to my appointment here in Oldenburg as a full professor, she became maître de conférence in the university in Lille, where she's now working in the Centre de Recherche en Informatique. And yes, we're looking forward to your presentation now, Sara, on set-based multi-sensor data fusion for integrated navigation systems.
I can start?
Yes, please go ahead.
Okay, so good afternoon, everybody. Today I will present my work, some work done on in University of Bordeaux when I was a postdoctoral research in IMS laboratory. This work was done in collaboration with Christophe Combastel and Alice Gadrich. This work is about a seat-based multi-sensor data fusion architecture for integrated navigation systems. So the outline of this talk will be as follows. I will start by a brief introduction, and then I will describe the multi-sensor data fusion architecture. I will give some simulation results, and I will finish this presentation with some conclusions and further works. So just to give you a little bit an idea about the context of this work. So this work was done in the context of a project which is called Cocotier, Concept de Copie des technologies intégrées en rupture. This is a collaborative project on new technologies for future intelligent cockpit in single pilot operations. This project was supported by the French Directorate General of Civil Aviation and has been coordinated by Airbus. So this project, in this project, there is a lot of partners, industrial one and academic one. And I was working, as I said, in the IMS lab in the University of Bordeaux. So the objective of the study within the Cocotier project is to provide a precise aircraft position in the runway frame. We chose the runway frame because in this study we are interested on the approach and landing phases of a flight. So we will provide an algorithm to compute a precise position of the aircraft. The inputs of our algorithms are data provided by several sensors. So we have an inertial reference system, which provide a 3D velocity. We have a global positional system GPS, which gives us a 3D position. And we have also an instrument landing system ILS, which provide us with the lateral and vertical angular deviations with respect to the runway frame. So for the validation, we will use differential GPS data, DGPS, which will serve as a reference and will be used, as I said, to validate the data fusion algorithm. So in the outputs, we will have the position X, Y, and Z expressed in the runway frame. So we have chosen to use the IRS as the reference sensor, which will define the state equation of our algorithm, because generally this type of sensors are already consolidated on board. That means that we have, for example, 3 or 5 IRS sensors, and then we will consolidate the data before being before being sent to other devices, but in particular our algorithm, which will be used for the data fusion. So we assume that we have the velocities in X, Y, in X, Y, and Z directions. And we consider that this velocity is expressed as a nominal value or the actual aircraft ready velocity. So VK0 in this case, and we assume that this velocity is subject to some noise, some measurement noise, which are defined by E multiplied by omega. This matrix E is a time varying matrix and will be computed later, and I will give you the procedure to compute this time varying matrix. So we will just use a simple integration to get the position X, Y, and Z using a given sampling time, and it is given by the equation 2. So our state, the state vector will be the position X, Y, and Z, and it will be calculated as given in equation 2. So we have, as I said, we have the GPMs, so we will define state space model. So the GPS give us the 3D position, and the ILS give us the aircraft vertical and lateral deviations. So the ILS is a system which is defined by two subsystems. The first one is the localizer, and the second one is the glide slope. So the localizer will provide us the horizontal guidance with respect to the center line of the runway, and the glide slope will provide the vertical guidance toward the touchdown point here. That's me. This is the touchdown point with the runway. So here I do not give the details about the equations. I will show them later here. So just these equations to relate the glide slope measurements and the localizer measurements to the state X, Y, and Z are computed using some geometric equations. So the measurement equation finally will be given as follow, as these two equations relating the glide slope and localizer to the state due to the position of the aircraft are nonlinear. So we have a nonlinear measurement model, and defined by the two measurement GPS and ILS. So this observation equation will be nonlinear and will be used later to perform the data fusion process. Just to mention that as for the IRS and all the sensor in general, we assume that we have some measurement noises, and this measurement noise is given by var theta k in this case, and the matrices F1 and F2 are time varying as well, and will be calculated later. So in this work, we used the Kalman filter to perform the data fusion, the multi-sensor data fusion. So we have as I said, we have some measurement noises, omega and var theta, and these noises are generally difficult to characterize. So we decide to use the seat membership techniques, in which, as you know, we don't have to put any assumptions about the probability distributions of these noises. We will just assume that these noise are unknown but bounded. So in the end of in the output of our algorithms, we will have the upper bound and lower bound of the position X, Y, and Z. So in this case, we just call that set-based data fusion, and we will use an extended Zonotopic Kalman filter. We assume that the measurement noises omega and var theta are bounded by a zonotop, a zero-centered zonotop. And we will, as I explained before, we will compute the matrix E and F. So we will have an online adaptation, an online tuning calculation of this time variant matrices, which will depend on the characterization of the noises related to all the pre-processed data. So the seat-based navigation, the seat-based multi-sensor data fusion scheme is given in this figure. So we have 3 sensors. 2 are used as measurements, and the IRS as a reference sensor. We will so in this part, all the data are expressed on the same frame. As I said before in the beginning of the presentation, all the data are expressed with respect to the runway frame, and all this change of coordinates and change of references are calculated and in this first stage. Then, when all the data are expressed with this in the same reference frame, we will send this data to some elementary filters. These elementary filters will be detailed in the following slides. So the objective is that this elementary filter will give us some features about the data, about the pre-processed data. These features will be described as a center and a radius. So it will be given as a confidence interval. Once we define the center and the radius of each data, pre-processed data, then all these informations will be sent to the seat-based data fusion algorithms, which will provide us the seat contain the seat enclosing the real estate, the position of the aircraft in our case. So for these elementary filters, as I said, so we will have in the end of this in the output, some features and useful informations from each scalar pre-processed signals. So in here, I just focus on the term each scalar data, because each scalar signals, because if I take, for example, the IRS, we have 3 velocities because we have in the 3 directions, X, Y, and Z. So for each velocity in each direction, we will have some features and some useful information that will be used later in the multi-sensor data fusion algorithm. So these elementary filters are defined based on a first order learned tuned model. I will explain later how we get this model. And then once we define our model, we will use a first order interval based algorithm to provide the center and the radius of each of these scalar data. So, so the first step is that to get a model-driven form describing each pre-processed data, we just use an equivalence between 2 models, between a data-driven form and a model-driven form. And this equivalence, as you can see here, is very simple. So we just consider a first-order low-pass filter. So we can see here it is a data-driven form. So just a filtering of our data, a filter of our data. And then using some transformations, we can easily get a model-driven form. This means we have a state equation and a measurement equation. These 2 models are dependent on some parameters, tuning parameters, namely F, which is the magnitude of noise, of error, and A, which is the decay time of our low-pass filter. So using this equivalence, we get our model with a state equation and a measurement equation, and we have some parameters E and F, which can be computed using some historical data. And then once our model is defined, we will use a first order interval based algorithms. This first order interval based algorithms is based or is inspired by based on EZKF, Zonotopic Kalman Filter, optimizing a first norm criterion. So compared to the classical ZKF, when we optimize the Frobenius norm, because we are in some vector space, in this case, we will just optimize a 1 norm criteria because we are using some scalar data. So in the end of our elementary filters layer, we will just get a center and a radius related to each scalar preprocessed data, preprocessed signals. So here I give the steps of the algorithm. So here, as I explained before, the inputs will be just the time of the filter, the magnitude of the noise, and the measurements. The output will be the center and the radius of each scalar measurement. So here, as you see in step 7 and 8, we compute the center and the radius depending on the parameters f and a, and it is a simplification of a EZKF in which we just optimize a first norm criteria. Then once we get our once we get the radius and the center of each scalar data, then we will go to the set-based data fusion process. So as I explained before, we have we have the state equations and the measurement equations. Remember that the measurement equation is a nonlinear one because we have some nonlinearities due to the ILS equations. So in this work, we will just, because of that, we call the algorithm an extended Zonotopic Kalman filter, because we will linearize the nonlinear observation function H with this function will be approximated and enclosed using some state membership techniques or some interval analysis techniques. So the state vector X can be represented by a center plus equal to center plus delta. This delta will be just dependent on the radius of this set enclosing the state, and using just a first order Taylor development, we can express this function, this nonlinear function H by the following terms. So the first one is just the evaluation of this function at CK. The second one is the Jacobian matrix, because generally we stop in these two terms, but in this work we also enclose the remainder of the first order Taylor development, namely the Lagrange term here will be enclosed, and then it will be also taken into account on the set-based data fusion process. So here, after some calculations, the remainder term here will be enclosed in a Zonotop as well, with a center CH and RH. This center and the radius will be computed using just as you know, this term, the R1 will depend on the half of the Hessian matrix, and then it can be bounded using the bounds of C, using the bounds of delta here. So after some calculations and developments, the measurement equation can be linearized as follows. So we can see here that we have a new linear measurement matrix C, which is the Jacobian matrix, and a new measurement noise, bounded measurement noise V hat K. This one is this vector will depend on the original measurement noise, but also on the radius of the remainder term that has been enclosed, and we have a punctual term here which will depend on some evaluation of the functions with respect to the center CK. So in this case, once we define the linearized model, we can use a data fusion. We can use for the data fusion. We can use this Zonotopic Kalman filter for the data fusion process. To return to the fact that the time varying matrices E and F will be updated online. The matrices E and F define the measurement noises, and remember that the elementary filters give us the center of the pre-processed signal data and the radius of the signals. This radius is calculated as I described it before, with respect to the magnitude of the error and magnitude of the noise. So all this, the noise related to the data can be described by the radius of the confidence interval given by our elementary filters. So these matrices will be defined as diagonal matrices and will depend on the radius of the data computed on the elementary filters. So once we get a data, once we get the data from the sensors, we will compute using our elementary filters. We will compute the center and the radius online, and this radius will be used later to compute the matrices E and F to characterize the noise related to this pre-processed. So here in this algorithms, we summarize the multi-sensor data fusion process. So we will, as I described before, we will compute using the Zonotopic Kalman filters. We will compute the center and the radius of the center and the radius of the Zonotop Z K, which includes the state vector X. And so here, this is the classical procedure to compute. So we have the optimal filter gain, and then we will just compute we will propagate the center and the radius of the zonotop, and then using the interval full formula, we can compute approximation of the zonotop, which can be used to compute an upper and lower bound of the state X at each time instant. So here I will give you some simulation results. So here, as you can see in the first layer of our architecture, so we have to define the maximum magnitude of errors, or the margin of errors F. So we define for the X, so for the IRS sensor, and for FY, which define the magnitude error of the two sensors GPS and ILS. So these magnitude of errors have been computed using using some historical data from the same sensors that we will evaluate in the simulations. So we just filter the data and then compute this margin error experimentally using all this real data, historical real data provided by Airbus. So once these parameters are defined, this is the simulation of the first using some data. So this is the first scenario. As you can see here, so this is the start and the end of our landing scenario. So we have, just to note that this is the real data provided by Airbus. All the simulations has been validated on this real data. So this is the first scenario. We have a landing. We have, so here the end is the touchdown point with the runway. And here we have the X, Y, and Z positions of the aircraft. And as you can see here, so in the red color is the data provided by the difference GPS, and in the blue, it is the upper bound, in the green, the lower bound. And as you can see, the GPS measurements are inside the estimated interval for X, Y, and Z. Here I just take us another scenario. So it is a landing one as well. We have the start point and the end point, which correspond to the touchdown point with the runway. And you can see here as well that the DGPS data are inside the estimated upper and lower bounds. So just to conclude this presentation, so the study was done to provide IRS, GPS, ILS seed-based multi-sensor data fusion algorithm. We used an extended Zonotopic Kalman filter to enclose the ILS nonlinearities, and all the simulations has been done on real flight data provided by Airbus. So this is a preliminary work, but you can also, if you are interested, to I put here a reference to work that has been published on a control engineering practice journal, and in which we have completed this work using a multi-layer architecture, in which we have also taken into account the fault-tolerant issues using a monitoring layer. So it is follows a little bit the same idea. So we have the pre-processing layer to express all the data in the same reference frame, and then the first layer, it will depend on these elementary filters that I presented in this work. In layer 2, we just put some fault diagnosis and fault tolerant fault detection algorithms, and in the end, the layer 3 we process. In this work, it is not seed-based data fusion algorithms, but we merge all the two aspects, seed membership and probabilistic one, and we have used others real data, other scenarios to validate the algorithms. There is a lot of simulations, and you can maybe, if you are interested, go to this reference, and you will have a very complete version of this work. Thank you for your attention, and if you have some questions, we can discuss.
So many thanks, Sara, for a very interesting presentation, and I'm pretty sure that we will have some questions. Now, let me see. Okay, the first reactions, I think, from Christina and Natalie are just an applause, the same from Carlos. Or Carlos, do you want to ask a question?
Okay.
Yeah, he wants to ask a question. Okay, please go ahead, Carlos.
Okay. Hi, do you hear me?
Yes.
Yes? Okay, perfect. First, thank you for your really nice talk. I really like it, and I think it's a really nice application in a real environment, actually. So that's something that is have a lot of future, definitely. And I want to make first one small comment. If you go for the slide 15, yes, this is just a small comment, just to say that I know what is that. The line 9 is not the computation. No, that one. The line 9 is not the computation of the radius. This is the generator matrix.
Yes.
So yes, it's not exactly the radius of the sonotone. That is something to take into consideration. And
yeah, I agree.
Yes, you should. Yes, that was just something really. Yes, that was just something really small. But something that I really like about this Zonotopic Kalman filter is that you can actually analyze the convergence. Something that we cannot usually do with other set membership approaches, with performing just intersection. That's something really nice. However, something that I don't like from Professor Combaster is about the interval hole, because he only reduced using the interval hole. Have you ever tried to consider another sonotopic order reduction method? On this method, yes, probably it's not going to be optimum, but it's not going to be optimum for another sonotopic order reduction, but it's going to be much better. So
yeah, for the moment we didn't consider another type of reduction operators, but yeah, I agree that the interval hole we just approximate. This is just an approximation of the intervals from the Zonotopic one, but we didn't use another type of approximation for the moment. But maybe we can. Yeah, this is the subject of this presentation, is also to get some remarks and then improve our results.
Yeah, definitely. And No. My point is about, for example, each time that you are moving, the line 9 is going to be increasing. So for that reason, you have the line 2 that is basically the reduction, and this reduction is basically on the just interval hole. Yeah. Right, using the norm 2. That is basically my point, because actually, and this is now self-promotion. Right now, we currently develop some Zonotopic order reduction that is quite efficient and is able to reduce the sets, and maybe we could try to make this approach a little more accurate in that sense. And yes, we still do not have the convergence proof for these methods using the Zonotopic Kalman filter, for example. But it is much more efficient, and we have the test, we have the results, and we can just share the code, and we can try to build in something together.
I would like to get maybe some references, and we can discuss this later. Yeah, if you can just, I will, maybe in the presentation I didn't put my email address, but I can share it in the
in the chat.
Yeah.
Yes, definitely, and let me send you also mine. And okay, that should be part of my question done. Thank you. It was quite nice presentation. Pleasure.
Okay, do we have any further questions? Okay, Fabrice?
Yes, I was wondering, can you tell us more about what is the underlying sensors inside what is called Inertial Reference System?
You are talking about this one?
Yes, about what is called the IRS. What is the physical sensors that are used inside that system? Do you know that?
Inside the Inertial Reference System, you mean?
Yes.
Yeah, it is like IMU. It is Inertial Measurement System.
Okay, so it's gyroscope accelerometers?
Exactly, yes.
Okay.
But as I said before here, generally in these aircraft systems, there is a lot of IMU or a lot of IRS systems, and then they use some algorithms to consolidate data before being used later. Because, for example, here the data that we use for the IRS has been already consolidated on board. So, for example, we can have several systems like this one, and then they consider using some algorithms. I don't have a precise idea about how they do that, but finally all the data are already consolidated online. Because of that, we use it as a state in the state equation or as a reference sensor.
Okay, and can you remind me which state variables of the aircraft you get just from the IRS?
The position and X, Y, and Z.
You already get a position estimate
from the IRS one.
Yes.
Yeah. No, we get just the velocity.
The velocity.
X, V, Y, and VZ.
And it's the velocity, the translation velocity, or
yes, translation velocity.
Okay, and so it means that it is probably computed from the accelerometers, or okay.
Yes, and because in here we don't we directly get the velocity x in the direction x, y, and z, but we don't calculate as the classical procedure from accelerometers and gyroscope. We have to use some transformation coordinates and then get the velocity and the position in the end. But in our case, we just assume that this sensor gives us the velocity in x, y, and z directions, and all this pre-processing has been done on board. So we don't we don't develop this part.
Okay, okay, I understand. And this part gives you also an estimation about the error of the velocity, or not? You have to choose the errors that might have this system.
Yeah, no, for the moment, yeah, in this study we just get the real data from Airbus provide us with a lot of scenarios with real data, but without giving us an idea about the error. This is why, as I said, that in the first layer we have to make some pre-processing to evaluate the magnitude of the error related to each sensor, because we have several scenarios, several data, but from the same device. So we can have an idea about the measurement noise about these signals.
Okay, and just probably last question. So you are only working with the translation of the aircraft and not about the rotation?
No, for the moment, no. We just consider these three sensors. We just focus on the translation velocities and translation position in the runway frame. So
okay,
we just give X, Y, and Z, but we don't, angular position are not. The angular in this case.
Okay, many thanks.
Thank you.
Okay, do we have any further questions? Yes. Xingzhou, I think it's yours.
Yes, if I'm allowed to ask.
Yes,
so also,
please go ahead.
Yeah, thank you. So also thank you very much for the nice and very interesting presentation. So I'm basically also working with GPS. So my question is something about GPS. So as I understand the input from GPS sensors is directly the position estimates. So I wonder about how precise is the solution, and what kind of technique are you using? Is it based on pseudo range measurements or carrier phase measurements?
For this part, I can give you a precise answer, because for the moment, this is the objective of our study. We know that the measurements from the IRS, GPS, and ILS are actually not accurate. So the objective is to make the data fusion and then get some precise position to be compared with the differential GPS. But actually, I don't know how this data will have been computed on board, or maybe because we are several teams to work on the project. Maybe there is some teams that works in the signal processing part, but for our case, it is just focused on the data fusion. So we get the data and then we make some. We make the data fusion and some pre-processing, but I don't touch this part. I didn't work on the signal processing part. So in this work, we just get the position, X, Y, and Z from GPS, and then we have to get a precise one compared to the DGPS.
Yes, so I think I got your idea. So I have a follow-up question. Also, it is a general question about the data fusion. Yeah. So do you have any assumption about the error distribution in your filters? And do you think it matters with the Zonotop, this site estimations? So because like in the statistical model of the filters, we have the point estimates, but in the Zonotop, you estimate both the point and also the radius. Yes. So in this case, is the error assumed error distribution matter in this case? or is it important to state an assumption in this case?
Yeah, I'm not sure that I understand the questions well. Do you talk about the error, right?
Yes.
How we can evaluate the error in the context of set membership techniques?
Mm-hmm.
Yeah, this is the question. Okay, so in here, as in this part, yeah, when we are in the probabilistic techniques, the problem is that we can't describe the probability distribution of the noise. This is a very big problem, not just in data fusion, but can be also in the state estimation using probabilistic techniques. So in another side, the set membership techniques can allow us to just describe the set of these noises. But the problem in the set membership techniques is that maybe sometimes we can have large solutions. So it is a very, can be sometimes conservative, because maybe we can put a big interval and the real error or the real noise have a very small magnitude. So we will lose the precision. But in our work in here, the objective is to introduce these elementary filters, and these elementary filters will give us an idea about the magnitude of the error. So all this noise will be defined as within the radius related to each scalar data. To each description will allow us to have an online update of the matrices E and F related to the noise. So because in the classical algorithms, the matrix E and F are fixed, so we just put an upper and lower bound about the noise, but we can't update them online. So in this work, we just get the data, we filter the data, and then we can compute the magnitude of the error and then update in the real time the matrices related to the noise. So here we just reduce the conservatism with respect to the case in which these matrices are fixed. So yeah, in both cases we can have some advantages and disadvantages depending on how we define these noises, which are assumed to be unknown but bounded, and in the other side, how we can describe the probability distribution. So we have to found a compromise with respect to the application, maybe, and also what we have in this position. For example, here this magnitude of errors are computed using a lot of historical data, so we have some idea about the magnitude of noise. But maybe in other applications we cannot have the real data or the historical data, so it will be difficult to define this noise. So yeah, I don't know if it is it responds to the question, but yeah, this is the answer, maybe, if I understand well the question.
Yeah, thank you. So I think the answer is quite clear. So
okay,
thank you very much.
Thank you.
Okay, at the moment, I do not see anyone else who has to raise their hand. Therefore, I would like to ask a question. Let's go to the slide 10 again. Because what you have shown there is that you have some kind of consolidation phase already that also makes sure that all the sensors provide the data at exactly the same time step.
Yeah.
Did you take into account also scenarios where the timing is uncertain? Where you have some imprecision in the time step where you have acquired the data? Maybe also some unknown delay in the sensor data?
No. No, for the moment, we assume that all the data are synchronized and there is no time delay. But yeah, in this type of applications, I think the time delay is always present, but it was not taken into account in this study. But yeah, I agree. But in yeah, in this study, we just assume that all data are arriving in the same time.
Yes, I think maybe for aircraft applications, this is not the really big problem because the transmission of the data is not really that difficult. I'm just thinking of, for example, underwater applications, for example, concerning also Fabrice's question, or Luc as an expert here in the audience. I think really where you have also problems of communicating huge amount of data in short time spans. Yeah. In such cases, especially some unknown temporal delay, also a missing synchronization would be very interesting and also challenging.
Yeah.
And maybe something, since also Carlos already advertised a little bit. I'm thinking maybe of another application that we could treat here, maybe also jointly with Carlos here in Oldenburg, because we have just recently bought a few Turtlebot robots. And I see also here in the audience a few of my colleagues here from our embedded hardware software systems group. And I think really it makes sense also in the frame of some multi-agent robot systems that we take into account such uncertainty also on the measurement time steps, and that we try also to extend your algorithm to such a setting. And we would right away have some test scenario where we have full access to data using some Turtlebot robots, where we could work on such thing together.
Yeah, we in our group, in Crystal. So the group when I'm working now, we are run. So we have always this. There is some PhD students who works on taking, namely this time delay into account in the control architecture. So yeah, it is a very challenging problem and very interesting problem, I think.
Okay, there are two questions. Okay, sorry, Mohammed, it's your turn, definitely.
Okay, can I ask the question? Okay, yeah. So thank you, Sarah, for this very nice talk. I have just some questions about the real-time issues. We know that the interval methods needs very high computation time. Did you evaluate the computation time in order to get the estimation of the position of the aircraft?
Yeah, actually, I didn't evaluate the time. The time computation, the time complexity of the algorithm, but it depends also on. Yeah, it is maybe the question of Carlos. It joined the question of Carlos about the reduction and the operator of the Zonotop. So if we reduce, it depends, because the reduction operation can also reduce the time computation of the algorithm. And I think because here the choice was done on, we chose to use the Zonotopic Kalman filters, which I think have less time complexity with respect to all the intersection algorithms. So for example, when we just talk about the seat membership and the Zonotopic seat membership techniques, which consist to, for example, to compute the Zonotop enclosing the state and the Zonotop enclosing the measurements, and then make an intersection. So all these techniques are a little bit very high with respect to the time computation. But I think in this type of algorithms, it is. Yeah, I think I didn't evaluate. I don't have the exact evaluation of the time computation, but I think it will have less and less, more or less computation time with respect to the other seat membership techniques.
Okay, sorry. Okay, because if for example, if you want to integrate this method into the control level, as Andreas and Carlos said, if we use Turtlebot, in order to control the Turtlebot in real time, we need to get the position fastly in order to integrate this part into the control part, which needs, I think, the observation part must have a small rising time in order to integrate all this estimation into the control parts. So because I face the same problem, I have developed one model predictive control, which is based on interval analysis. And this model predictive control needs a huge computation time, which prevent us to validate it in real time. So we have to make the control part in offline to get all the control variables, and then we inject them offline into the control system, which is not adequate.
I agree.
Level.
For the moment, all the interval techniques are difficult to apply in real time for the moment. Because of that, we have less algorithms which are using actually in the industry or in the real applications. We have less algorithms using this kind of techniques. We have to put an effort to reduce the time computation more and more, but
Okay, wait, sorry, I want to make a comment here because actually I am against what you are saying, because I consider that this is extremely fast. This is just an algebraic, and this is an explicit formula. I mean, we can have some problem with the computational time when we are increasing too much the dimension. And in those cases, yes, we have some increment, but we have technique for reduce that. And these techniques are explicit. I mean, this is a little bit different when we try to study the constraint sonotone, where you have some optimization problem inside. And when you have this optimization problem, is probably could take some problem, but the complexity of this is not M. I mean, it's not even N by M. No, it's just M. It's based on the number of generators. So it's quite fast. It's very, very fast because it's just explicit formula. You just use it and it's quite fast. And most of the interval methods that I know of so far, because I don't know too many interval methods, not Zonotopic or something like that, they are also very fast because they are explicit. And with the problem that you have, Mohammed, I think is, and if you work with Zonotopic, because I think I had the same problem, and it was about the computation of the maximum point, because you need to compute the vertices, and that is a different problem. And there are really nice techniques to implement it. For example, you can take like the constraint of your system, and you just can try to maximize to your Zonotopic. So he's gonna just end with some vertices. So you're not gonna need to apply. You're not going to need to check all the vertices. You're not going to need to apply one or two vertices. That's a different one, and that's something that I like from these approaches. Yes, we have too many lags, but I think that the computational time is not one of them, in my opinion. But I want to make...
It depends also on the kind of techniques used, because there is actually some optimization problems that are solved online. So it will be very, very difficult to be implemented on real time. So it depends. Generally, the Kalman filter or the Zonotopic Kalman filters are less, have less computation time with respect to the other techniques. But there is some people who, for example, solve some LMIs online to compute these Zonotopic techniques. This is hard in the computation time, but as I said, it depends on the because a lot of techniques exist, so it depends on which one is used.
Okay, actually, yes, you're right. And yes, Alamo 2005 is an explicit formula, and he get after that, in Alamo 2008, one with some optimizations. And this is with optimization is a little bit more complex. And I want to actually ask some, because before that I interrupt Mohammed, I wanted to ask another question regarding what Rahul said, that Andreas already said, and it was about the different sampling time. And I want to ask a really naive question, and is, where is this data feature estimator, what is this place? I mean, this is on the aircraft or this is on the control tower?
No, it will be in the aircraft controller. because
inside the aircraft.
Yeah, maybe I didn't precise this, but the idea of this product is to perform autonomous landing. So the objective is that the aircraft use the data fusion algorithms to fuse the data and get the precise position in X, Y, and Z with respect to the runway where we will land, and then so it will be implemented in the aircraft, in the controller of the aircraft.
Okay, and I'm not completely sure about the rest of the. I haven't maneuvered ever an aircraft, so but I can imagine that they have a lot of sensors and a lot of variables. So it's not hard to understand that maybe you can have some problem with the traffic of the information because you could have too many. So have you, or do you know if there are some event trigger, self-trigger mechanism apply into this kind of systems?
In the context of our project, or at least in the work that was done, we didn't take into account the event triggered techniques, but yeah, because in this work we are limited. We just use 3 sensors, but there is also some altimeter sensors and other sensors that can give us also the position in X, Y, and Z. So the objective is to gather all these sensors and to perform all the data fusion with respect to all available informations. So as you know, as you said, introducing some event triggered techniques will be beneficial because we cannot at each time instant compute the position X, Y, and Z, because as you know, we have the dimension of the aircraft and the displacement. It will depend on the time instant in which you calculate the X, Y, and Z, and maybe we can just depending on some events perform the computations, especially if this computations take a lot of. This is some bounds that can be also done on this kind of applications.
Thank you. I think that's really a great outlook that you just mentioned, for example, also to work in some event-triggered framework at the end, to work on, let's say, reduction of the computational complexity just as by reducing the amount of data that you have to process. Exactly. This is definitely something worth to be investigated in future work. Yeah, okay, then having a look at time constraints, I think it's time now to thank Sara again for the very interesting presentation. Also, thank you to all of you for a very intense discussion with lots of insights that you have provided. And yes, at the very end of this seminar today, I just thank you for attending the session today. We will put the slides of today's talk on the webpage that you can also have a look at the references that Sara has quoted. And yes, the only thing that is now left to me is, as usual, I wish all of you a nice Friday evening, Friday afternoon, maybe even Friday morning to some of you. And yes, let's see each other again very soon on Friday in 2 weeks for the next seminar, which will be given by my colleague Robert Dehnert from the University of Automatique.
Okay, thank you very much.